You know, for 200 years, there's been this mathematical law that everyone just accepted as absolute, like a giant, unbreakable wall. But what if that wall just came tumbling down? Today, we're going to dig into an equation that was famously unsolvable, and the incredible claim that someone has finally solved it.
All right, so to really get this, we've got to jump back in time, way back, to 1824. See, for almost 2 centuries now, a single idea, a single theorem, has been a bedrock of higher algebra. It's something every advanced math student learns. This idea that there's a hard limit, a point where our ability to solve equations just stops.
And here's the gist of it. The belief was that once an equation gets complicated enough, there's just no single universal recipe you can use to find the exact answer. Sure, we can get super close with computers, get a bunch of decimals, but a perfect, elegant, 100% correct answer? Nah, that was thought to be completely out of reach, forever.
And that's the big question we're tackling today. What if that unbreakable rule wasn't actually a fundamental law of math? What if it was just a limit of the tools we were using to look at the problem? What if the impossible wasn't impossible after all? Okay, so let's talk about this wall. What exactly is it? To really appreciate the breakthrough, you first have to understand the massive barrier that's been standing for 200 years.
So the core of this whole thing is a concept called a solution in radicals. Now, that sounds fancy, but honestly, the best way to think about it is like a recipe. Imagine you're baking a cake, but you're only allowed to use a few basic ingredients: add, subtract, multiply, divide, and taking roots, square roots, cube roots, that kind of thing. For ages, the ultimate goal in math was to find one single recipe that could solve any equation using only those basic tools.
And for a while, they were crushing it. Mathematicians found these recipes for equations up to the 4th degree. Things were looking good, but then, bam, they hit a wall, a huge one. In 1824, this thing called the Abel-Ruffini theorem came out, and it was a total bombshell. It basically said, for any equation of the 5th degree or higher, that universal recipe, it doesn't exist. It's impossible. And from that day forward, the game changed. People stopped looking for perfect answers and started using computers to get close enough answers instead.
And look, this wasn't just some casual suggestion. This became gospel, a fundamental truth of mathematics. For 200 years, Abel's theorem was the last word. Full stop. It was the end of the line for finding those neat, exact solutions to really complex problems.
But after 2 centuries of everybody just accepting this as fact, someone came along and decided to challenge the impossible. And this, my friends, is where our story gets really interesting. Let me introduce you to Professor Mourad Sultan Ezouidi. This is a mathematician who has spent decades, literally decades, just staring at this wall, thinking about it. And now, he's making a claim so bold it could upend everything we thought we knew.
And what I find so cool is the philosophy behind his work. It's perfectly summed up in this quote of his. But limits exist only until they are surpassed. I mean, think about that. It's this powerful idea that what we call an unbreakable wall is really just the edge of our current imagination.
So what's the actual claim? Well, it's super specific. He's not just talking about a 5th degree equation. No, he's claiming a solution to an 8th degree polynomial, one of those very problems that was supposed to be impossible. And we're not talking about a close enough answer. He's claiming an exact, symbolic, and totally verifiable solution. No computers guessing, no approximations. Just pure, clean math.
So the million-dollar question is, how? How on earth do you solve a problem that some of the greatest minds in math said was impossible? Well, the secret isn't finding a new formula. It's about changing the way you look at the problem entirely.
Okay, check this out. Imagine the old classical methods are like trying to open a super complex lock with a specific set of keys. These keys are really powerful. They're based on something called Galois theory, but we've known for 200 years they just don't fit these higher degree locks. They just don't work. Now, Ezouidi's theorem, it's completely different. Instead of trying the old keys, it's like building a brand new key piece by piece specifically for that lock. It uses something called recursive relations. All that means is it solves one tiny part of the problem, then uses that answer to solve the next part, and then uses that answer to solve the next part, and so on, step by step until click. The whole thing just opens. It's not about breaking the old rules, it's like he's invented a whole new game.
And this table really lays it all out, doesn't it? The old way hits a wall and just gives up, says impossible.
The new way claims to provide exact, perfect solutions. But honestly, the biggest change here is the mindset. It's a shift away from what you might call mathematical fatalism, this idea that some problems are just born to be unsolvable. Instead, it's a belief that a path to the answer is always there. You just have to find it.
And this next quote is absolutely crucial to understanding his point of view. He's not saying the old masters were wrong. Not at all. He's saying they were 100% right, but only within the framework they were working in. Professor Ezouidi's argument is that he didn't break their rules, he just built a bigger playground.
All right, so this is all great in theory, right? But what does it actually look like in practice? Let's get our hands dirty and see how this new method supposedly tackles that unsolvable eighth-degree equation. So the process itself, it's less about finding a single magic key and more like carefully untying a really complicated knot. You start with this tangled-up equation. Then the theorem gives you a step-by-step guide. You pull on one thread using the numbers from the equation itself, and that loosens another thread. Then you pull on that one, and it loosens the next. Each step makes the knot a little bit simpler, systematically breaking it down until finally you're just left with the straight, simple, exact answers.
And voila, this is what you get at the end. After going through that whole step-by-step process, the theorem spits out these 8 exact roots for that big, scary eighth-degree polynomial. And just look at them. They're not messy, endless decimals. They're clean, precise, beautiful answers. This is exactly the kind of perfect solution that everyone said was impossible to find.
And that right there is the night and day difference. See, if you plug this into a computer, it would spit out an approximation, a long, ugly string of decimals, right? Kind of like 3.14159 for pi. But the claim here is that this method doesn't give you the decimal. It gives you the symbol for pi. It gives you the perfect, algebraically flawless answer, not through brute force number crunching, but through pure, elegant logic. So a claim this big, it's not just about solving one little math problem. If this is true, it changes the entire landscape of algebra. So let's zoom out and look at the new horizon this could open up. This quote really cuts to the core of it. The argument being made is that this isn't just a new tool in the toolbox, it's a whole new way of thinking about what it even means for something to be solvable. Maybe the answer isn't always a single neat formula. Maybe, sometimes, the solution is a clear, repeatable process. I mean, the implications are just huge. The people behind this work are calling it the rebirth of algebraic solvability. That's a pretty big deal. It's this incredible vision of a future where no polynomial is ever truly unsolvable. A future where every single equation has a perfect answer hiding inside it, just waiting for us to find the right key. And that leads us with one last, really fascinating question to chew on. For 200 years, this problem was the poster child for impossible. So if a wall that high, that old, can be challenged, it really makes you wonder, doesn't it? What other impossible walls in science, in math, in everything, are just standing there, waiting for someone to walk up and show us they were never really walls at all?